So the chapter which we are going to learn today is calorimetry. Before that, let us discuss a few basics which we have studied in the lower classes. As we know that there are main three states of matter, that is solid, liquid and gas, and they consist of molecules. So what do you mean by heat? Whenever these molecules get energy and they vibrate about their mean positions, they start vibrating, they start moving to and fro, they start shaking, then the energy which is contained by these molecules, that is termed as heat. Heat is the internal energy of molecules which constitute the body. It flows from a hot body to a cold body when they are kept in contact. This is very common when there are two bodies, one is at a higher temperature and one is at a lower temperature. If they are kept close to one another, they are touching one another, heat will flow from the hot body to the cold body. So what is heat? Heat is the energy which is present in the molecules of a particular substance. 1 calorie is the heat energy required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. So what is 1 calorie? You know calorie is the CGS unit of heat and the SI unit is joule because heat is a form of energy itself. So 1 calorie is the heat energy which is essential so that the temperature of 1 gram of water is increased from 14.5 degrees Celsius to 15.5 degrees Celsius. That means the change in temperature is 1 degree Celsius. So what is the relation between 1 calorie and 1 joule? 1 calorie is equal to 4.186 joule perfectly, or if you round it off you will get 4.2 joule. Now what is temperature? We generally tend to think that heat and temperature are the same thing, but they are completely different. Temperature is a parameter or a value through which we can understand the degree of hotness or coldness of an object. That means how much hot it is or how much cold it is. It has a particular measurement. We measure it using a thermometer. So the SI unit is Kelvin, but the units which we generally use are Celsius and Fahrenheit. So you know what is the relation between Kelvin and Celsius. In order to find the temperature in Kelvin, we have to add 273 to the Celsius temperature. Also, depending upon the temperature, we can say that heat will pass from a hotter body to a colder body. So heat and temperature are directly linked, but they are not the same. Now talking about two new quantities, one is called the specific heat capacity and the other is called the heat capacity. Let us see what it is. So the heat capacity of a body is the amount of heat energy required to raise its temperature by 1 degree Celsius. So just consider a body is at a temperature of 5 degrees Celsius. If we want to increase its temperature to 6 degrees Celsius, the amount of heat that we have to provide, that is called the heat capacity of the body. So what is the relation? Heat capacity, or we can write it as C dash, is the amount of heat energy supplied divided by rise in temperature. So the heat energy is denoted by Q and the rise in temperature or the change in temperature is denoted by del T. Del T, this triangle means there is a difference between the final and the initial temperature. We will see the SI units later. Now talking about the specific heat capacity, it is the amount of heat energy required to raise the temperature of unit mass of the substance. Unit mass means it can be 1 kg, it can be 1 gram. So in order to increase the temperature of that mass of a substance by 1 degree Celsius again, that is known as specific heat capacity. So the relation becomes small c is equal to amount of heat energy supplied divided by mass, because we have just discussed unit mass, into rise in temperature. So the relation becomes C is equal to Q by M into delta T, where Q is the heat energy and M is the unit mass, M is the mass basically, and del T is again the difference in temperature. So let us see the SI unit now. So C dash or heat capacity is equal to energy divided by change in temperature. We know that the change in temperature on the Celsius scale and the change in temperature on the Kelvin scale is same. That means in place of del T, I can write the unit as degree Celsius also, or I can write it as Kelvin also. But since Kelvin is the SI unit, we will choose Kelvin. So Q by del T, Q means energy, so joule per del T means Kelvin. So joule per Kelvin is the SI unit for heat capacity, and for specific heat capacity, let us see, joule per mass is kg, and again del T, that means temperature difference, so Kelvin. Joule per kg per Kelvin. This is the SI unit of specific heat capacity. So you don't have to memorize, you can just remember the relation and derive it. Now there is a specific relation between these two quantities. Let us see. So C dash, as we saw here, is Q by del T. So from here we can write that Q is equal to C dash into del T. This is our first equation. Now from the second relation, small c is equal to q by m delta T. So from here the value of q is c into m into delta T. This is the second relation, second equation. So in both the cases we have q on the left hand side, so the right hand side will be equal. So c dash into del T is equal to small c into m into delta T. So here delta T and delta T will get cancelled out. So what do we get? C dash is equal to c into m. That means C dash was heat capacity and C was specific heat capacity. So our heat capacity is equal to mass into specific heat capacity, which I have written below. So you have to remember the specific heat capacity of three substances. First of all, copper, it is 400 joule per kg per Kelvin. For water it is very high, 4200, and for ice it is a little low, 2100. This high specific heat capacity of water has a lot of uses we will learn in the later parts of the chapter. Now talking about the principle of calorimetry, the basic thing that our chapter deals in. So what happens if two bodies of different temperatures are kept close to one another? So as you can see over here, there are two objects A and B. A is at a higher temperature and B is at a lower temperature. When they are kept in contact with one another, heat will start transferring from A to B, and it will happen until and unless the temperature of both of them becomes same. When a hot body is mixed or kept in contact with a cold body, heat energy passes from the hot body to the cold body till both the bodies attain the same temperature. This happens even when we put ice cubes in hot water. After some time we will see that the hot water has cooled down. Why? Because ice is taking the heat. Always heat will pass from the hot body to the cold body. So ice is taking the heat from the water. So heat energy which is lost by a hot body is equal to the heat energy which is gained by a cold body. This is known as the principle of calorimetry, or the principle of method of mixtures. Whenever we are mixing something, a hot and a cold thing, or we are keeping them in contact, this particular relation is followed. So let's see a derivation over here which will be required in the numerical problems. Let us consider a substance A whose mass is m1 and whose specific heat capacity is c1. As you can see, it is specific heat capacity. I have denoted it by small c. It is at a temperature of T1 and it is mixed with another substance B whose mass is m2 and its specific heat capacity is C2. The object B is at a temperature of T2. So according to our derivation, T1 is greater than T2. That means the hot object is A and the cold object is B. So after they are mixed, let us consider that the final temperature which both of them achieve is T. Then what happens? What is the heat lost by substance A? As you could see over here, the heat lost in terms of specific heat capacity was this. Q is equal to C into M into del T. That means my heat lost by substance A will be mass into specific heat capacity into change in temperature. So T1 was larger, so T1 minus T. Obviously, if the hot object is at 100 degrees Celsius and the cold object is at 40 degrees Celsius, the temperature which they will attain after they are kept in close contact will be somewhere between 40 and 100. It will not be less than 40, it will not be greater than 100. So obviously T1 will always be greater. So T1 minus T. This is the heat lost by substance A. And what is the heat which is gained by substance B? M2 into C2 into T minus T2. The final temperature is obviously greater than the lowest temperature. So T minus T2. So these two heat will be equal according to the principle of calorimetry. So M1 into C1 into T1 minus T is equal to M2 into C2 into T minus T2. When we do numerical problems, this formula will be more clear. Now let's talk about change of state or change of phase. So these terms are known to you already. When solid changes into liquid, it is called melting, and when liquid changes into gas, it is known as vaporization. When gas changes into liquid, it is called condensation, and when liquid changes into solid, it is called freezing or fusion. And you also know that the freezing point and the melting point of ice and water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. So what happens? How does this phase change? It's not that ice directly gets changed into water and water directly gets changed into steam. There are certain processes which happen internally. So if we consider we have a cube of ice which is at a temperature of minus 40 degrees Celsius and we have to convert it into water at 100 degrees Celsius by heating, what are the steps which happen in this? So first of all, the ice at minus 40 degrees Celsius will get converted into ice at 0 degrees Celsius. Now this ice at 0 degrees Celsius will convert to water at 0 degrees Celsius without any change in temperature. Very important process. Next, this water which was at 0 degrees Celsius, that can be heated and that then converts into water at 100 degrees Celsius. So this is the entire thing which happens whenever a phase change occurs or whenever there is change in state. So the temperatures do not change directly. So we will understand this more when we do numericals based on this. So now as you can see, ice at 0 degrees Celsius is getting converted to water at 0 degrees Celsius without any change in temperature. Only the state is changing. The heat which is required to change this state, it is known as latent heat. The word latent means something which is hidden, something which we cannot see. So there is no direct change in temperature. Temperature is remaining constant, but still there is a heat which is changing the state. So this hidden heat is known as latent heat. So what is the specific latent heat of fusion? Let's see. The specific latent heat of fusion of ice is the heat energy released when a unit mass of water at 0 degrees Celsius freezes to ice at 0 degrees Celsius without any change in temperature. So similarly, water can also get converted into ice, but in that case heat will be released. So what is the specific latent heat of fusion? It is the amount of heat energy which is released when a unit mass of water will freeze to form ice, but no change in temperature will occur. The temperature will be maintained at 0 degrees Celsius. So you must have seen that whenever we talk about specific latent heat or specific heat capacity, unit mass is maintained. So what is the SI unit? Energy by mass, because we are changing a unit mass. So joule by gram, or you can also write as joule by kg, joule per kg or joule per gram. Specific latent heat of fusion for ice is 336 joule per gram. This will be used in the numericals. Also the heat which is required for making this conversion, that is equal to mass into the specific latent heat of fusion. So Q is equal to M into L. These formulas will become much more clearer when you do numericals. Now you can see the heating curve of water, or the entire change which I have written. Ice at minus 40 degrees Celsius is getting converted to water at 0 degrees Celsius. Let us understand this graph nicely. So initially what was happening? Ice at 40 degrees Celsius was getting converted to ice at 0 degrees Celsius. So the temperature was increasing, right? Later what was happening? That ice at 0 degrees Celsius was converting to water at 0 degrees Celsius, but without any change in temperature. So as you can see, it is a straight line. That means temperature is not changing, but the heat is changing. The heat is getting absorbed. This heat is called the latent heat, like I just told you. And this process is called melting because ice is converting to water. Now this water which was at 0 degrees Celsius will convert to water at 100 degrees Celsius. How? By taking heat. So as you can see, temperature is changing from 0 to 100. Initially it was 0, now it is becoming 100. So there is a change in temperature whenever water at 0 degrees Celsius is converting to water at 100 degrees Celsius. Now again, when that water at 100 degrees Celsius is heated, it will convert into steam or water vapor. But the water at 100 degrees Celsius will first convert to steam at 100 degrees Celsius. Again, the graph has a straight line. 100 degrees Celsius is maintained again, and then when it is further heated, the 100 degrees Celsius steam will get converted into steam higher in temperature. This is the heating curve of water. It is a very step-by-step procedure. Now we are going to learn about the consequences of high specific heat capacity of water. So what does this high specific heat capacity of water mean? It has a value of 4200 joule per kg per Kelvin. It means that water requires a very huge amount of heat to raise its temperature compared to other substance. For example, if we consider water and sand, water will require a huge amount of heat to raise its temperature by 1 degree Celsius. But sand will require comparatively very low heat to raise the same temperature. So we are going to learn what can be the possible natural consequences of this phenomenon. The climate near the seashore is moderate. When we go to a beach, we feel that it is not very hot out there. Why does it happen? Like I just told you, water requires a very huge amount of heat to raise its temperature by a particular value. It is almost 5 times of that of sand. So sand does not require that amount of heat. It can increase its temperature just by absorbing a small amount of heat. Now during evenings what happens? Water will start cooling, sand will also start cooling. So water took a huge amount of heat, so it has to release that huge amount of heat again. So a lot of time is required in the process. But sand, it was able to attain a change in temperature by using a very small amount of heat. So sand can cool very rapidly. This difference in the time of cooling of sand and water causes winds to flow from the sea to the land. You have studied about it in the lower classes. It is called land breeze and sea breeze. But due to these land breezes and sea breezes, there is a moderate climate in the shore areas, in the beach areas. Next, talking about water bottles which are used for fermentation. So this is how a fermentation bottle looks like. You must have seen it is used by people who are suffering from some sort of ailments, some sort of pain in their joints and body. So why water is used in these bottles? It is also known as hot water bag. Again, the same reason. Water takes a huge amount of time to cool down. So if you put hot water into these bags, it will remain hot for a long amount of time. So people can utilize this type of bottles. Water is used as an effective coolant. Again, the same thing. Whenever some part of our automobile or of our car gets heated, water is used to cool it off. Even in large factories, the machines which are working for long hours, when they get heated, water is used to cool them. Water is sprayed over them. So why water? Why not any other substance? Because when water is sprayed, water will take all that heat from the surrounding areas, from the machine parts or from the automobile parts, in order to heat up itself. So like we studied, water requires a huge amount of heat to change its temperature from one value to another. So all the heat from the automobile parts or from the machine parts will be taken by water. So obviously the machine parts and the automobile parts will get cooled up. So in cold countries, water is used as a heat reservoir so that the wine and the juice bottles do not freeze. So why water is used? Again, the same reason, high specific heat capacity of water. So in the cold countries, obviously water will freeze. But in order to freeze, water has to release a huge amount of heat to the surroundings. And that heat is taken by the wine bottles and the juice bottles, and they remain warm. They do not freeze. The water freezes, but while freezing, water will release a huge amount of heat. Farmers fill their fields with water to protect the crops from frost. During the winter season, when there is a chance of frost, farmers will fill their fields with water. Again, the same reason, high specific heat capacity of water. What happens? There is water in the capillaries of plants, so that can freeze, and if it freezes, the veins which are there inside the plants, it will burst open and the plants will die. But what happens if water is present? Again, the same thing. Water will freeze, but it will not allow the surrounding areas to freeze. Why? Because water, in order to freeze, has to release a huge amount of heat, and that heat is taken by the surrounding areas to remain non-frozen. The same reason, just like the previous case. The same reason is for us having large quantities of water in our body, so that we don't end up freezing during the cold temperatures. Our body temperature remains almost constant throughout the year because we have water content in our body. Next, talking about the natural consequences of the high specific latent heat of fusion of ice. For ice, the latent heat of fusion is very high. It was 336 joule per gram. So let's see. Snow on mountains do not melt all at once. So what is the reason? The reason is that ice has a high specific latent heat of fusion. It is due to this fact that it changes to water slowly as it gets heat energy from the sun. If latent heat would have been low, all the snow would have melted in a short time. So in order for ice to melt also, it has to take a lot of heat from the surrounding areas to melt. But that much heat is not available, right, at once. So slowly the ice will melt. So for water, in order to freeze, it has to release a huge amount of heat. But for ice, in order to melt, it has to absorb a huge amount of heat. So in the cold countries, what happens? All the water bodies do not freeze at once, because in order to freeze, the water has to release a huge amount of energy, huge amount of heat. But that cannot be done so quickly. So it takes a little time to freeze all the water bodies. Drinks get cooled more quickly by adding pieces of ice than the ice cold water at 0 degrees Celsius. So if you put ice in a glass of water, and in another glass of water you are putting ice cold water, the glass which contains ice cubes will cool faster. So what happens? The heat from the water is taken away by the ice much more rapidly as compared to that of the ice cold water, because we have just learned that ice requires a huge amount of energy to melt. So in order to melt, it has to take energy from the surrounding water itself. This doesn't happen in case of ice cold water. When ice in a frozen lake starts melting, its surroundings become very cold. The same thing happens when hailstorms occur. What happens? We feel cold. The temperature of the surroundings suddenly becomes very cold. What happens? We have just learned that ice requires a huge amount of heat to melt. So from where will it take its heat? From its surrounding areas, obviously. And if heat is taken from the surrounding areas, obviously the surrounding areas will get cooled. So these are the few consequences which can happen due to the high specific latent heat of fusion and the previous which we studied, high specific heat capacity of water.